Okay, bonjour, merci d'être venu. Welcome. Thank you for coming. So there's one thing I forget to say every time. When we did dynamical mean field theory, I wrote this big matrix and I used it to write an effective equation for just the GFF. But I want you to notice the analogy with the harmonic oscillator at the very beginning, right? Where I had a bat of just ordinary harmonic oscillator that came as damping into the into the harmonic oscillator that we were interested in. Okay, so today we start the last section, broken symmetry, and so I will first show you that try to convince you that broken symmetry is a very important principle of condensed matter physics. And I'll show you 3 examples. And then I try to discuss what this implies from the point of view of either the free energy or the ground state, quantum ground state, like within the tunneling and so on. And then the mathematical objects that are related to this notion of broken symmetry that come out very relatively easy are the concept of order parameter and Landau theory. And then we will try to do this in the context of the ferromagnet, which is a simple example, the itinerant ferromagnet. So I'll start with the variational principle, Feynman, Pals, Bogoliubov, lots of names associated with this variational principle that I will use for the ferromagnet, using this notion of order parameter that we have discussed here, and show you that mathematically one recovers the so-called gap equation and Landau theory that I will have discussed here in this context. And the variational principle, I'll give you the proof at the end, okay? So that we don't, I want to justify that we need it. Okay, so, okay, broken symmetry. I give you 3 examples. So let's start with the water-ice transition. So if we look at water, the atoms can be anywhere, right? But if we look at ice, so when the water is solidified, and we had that phase transition yesterday here, or the day before, if you look at the ice, then what happens is that if you look at the interaction between water molecules, so let me write this as V of R. I mean, it's not isotropic, so it's really a sketch, but you know that there will be some attractive potential like this. And so in the ice case, the atoms place themselves at this minimum. Well, there are small vibrations, but they are at this minimum. And in the ice phase, we have broken the symmetry of the water phase, in the sense that in water, if we look at one point and we find an atom, we have no idea if we look at some other point whether there will be an atom or not. Okay. But in the ice, once we have an atom here, there's a fixed lattice spacing, and we can look very far. And if we look at an integer number of times the lattice spacing, we are sure to find an atom. Okay. So we have broken the symmetry of the water phase. The water is very symmetrical, and the ice does not have this translational invariance that water has. Now, to know that there is an atom here, I need to break the symmetry also, in the sense that I need to choose where one of the atoms will be, and then the other ones are fixed with respect to that. But that's easy, right? You can look at any small interaction with the outside world or some impurity that will pin where the atoms are, and you're done. So we have broken symmetry. And for that we need a small external field. Once we have pinned where the location is, then we can let the small external field go to 0. Then another consequence of this broken symmetry is the rigidity. What do I mean by this? So if you look at water, take a bucket of water and plunge your hand slowly in the water. It will make some small waves and then it will disappear, right? Now suppose that you take the same amount of water and you freeze it in the form of a table, okay? With the legs here and the rest here. So now I have the ice. What happens if I push here? Well, the atom here will know that I have pushed here and everything will go up here. Okay, so there's a rigidity. And there's something that did not exist in water that exists now. It's shear waves, right? So if I take well, I mean, this is a zero frequency shear wave. If I take a solid and I can add I start to move it like that, there are eigen frequencies and it'll start vibrating this way, right? But water will not do that. Right? Water does not, I mean, it's what I was mentioning earlier, it's damped, it's over damped if you want. But here the shear waves exist. And the shear waves in some ways are trying to restore this symmetry in the sense that, you know, I can make the thing go around. So these are called goldstone modes. So when you break a continuous symmetry, so here the symmetry that's broken is translational invariance and rotational symmetry. So this, when you break a continuous symmetry, you always have these goldstone modes that come in. So we need a small external field, rigidity, and shear waves. So let's take another example. So we can do a purely electronic example. Here, perhaps I should mention right away, we are minimizing the free energy, right? So there's E minus Ts. So clearly, we minimize the energy if all the atoms are in this potential. Let's think classically now. So the energy is minimized when all the atoms are located at the same distance from one another. But then there's not much entropy in this. But in water, where the atoms can be anywhere, there's lots of entropy, right? So at high temperature, entropy wins and you have water, and at low temperature, energy wins and you have ice. Okay. Now let's look at the purely electronic case. So we look at density waves. So let's suppose I have a lattice. So I've broken this symmetry already. I'm focusing just on electronic properties. And let's take this as a we could take it as a field actually. Let's take it as a field, but so there's one atom, one electron per atom, and then there's a single term V, that's a near neighbor repulsion. And let's think at t equals 0, just quantum mechanics. So if the near neighbor repulsion is small, kinetic energy will win, right, in the energy. So we just have the electrons can be anywhere. Now suppose that the V, or the near neighbor repulsion, is enormous. What will happen? Right? The electrons will occupy this. Even if there's a U, a repulsion, if V is sufficiently strong, this will happen. So here, what do I have? I have a charge density wave. And instead of having electrons everywhere, the same concentration on every site, now they are located every 2 sites. So I've broken a symmetry, but now it's a discrete symmetry in the sense that they are either, I mean, I could have the lattice in registry here, or I could have translate everything by one lattice spacing, right? So I just had to choose where I put the first couple of electrons, and then the rest is determined. So I still need this small external field. I have the rigidity in the sense that if I push these 2 electrons here to this side, everything will move, right? So rigidity I have. I needed the small external field, the rigidity, but I don't have the analog of shear waves, because here the symmetry that's broken is discrete instead of continuous. So no goldstone modes for this. Okay, now a third example. We think of the ferromagnet. The itinerant ferromagnet. So let's suppose that we are at the bottom of a band, so not at filling, just at the bottom of a band, and with a few electrons here, and there's a large U that's present. So what will happen? If there's a large U, if U is sufficiently large, you see that the solution will be that I put all the electrons with the up spins, or down spins, or right spin, or left spin, or whatever direction. Why is that advantageous? Well, that costs a lot of kinetic energy, right? Because now I need to put, instead of having, a dispersion relation for up electron that's the same as for down electrons, and the Fermi energy is this. Now I just have the up electrons, so the Fermi energy will be larger, right? So I'm losing kinetic energy. I'm doing this, yes. It costs me a lot of kinetic energy. But then when the spins are all up, the potential energy is 0. If you think of I'm thinking of the Hubbard model, I should have mentioned U, right? Because of the Pauli principle, now they cannot step on each other. So I just fill the Fermi C. It costs a lot of kinetic energy, but I gain a huge amount of potential energy. So I need a small external. So I've broken a symmetry here. I've chosen a direction for the spins. Okay. Now I need a small external field for that. Okay, the small external field will decide where one of the spins point, and all the others will point in the same direction. I have a rigidity also. I have spin waves in this. The spins are all up. If I try to move this one here, a slight amount, then there will be, this one will feel it. It will feel it through a spin wave. Okay, spin wave being just this oscillation of the spins or precession. Okay. So I have the small external field, I have rigidity, and I have a goldstone mode, in the sense that if I look at Q equals 0, so it's uniform, then I can rotate the whole system. It sort of restores the symmetry in some sense, and it costs no energy. In the same way here that at Q equals 0, I could just rotate or move the whole solid. Okay. And here the symmetry I was breaking is continuous. These are not Ising spins. These are, real spins. They can point in any direction. So I've broken a continuous symmetry here. The continuous symmetry that's broken is continuous. The symmetry that's broken is continuous. I need a small external field to decide where I go. The state that I obtain is rigid, as rigidity, and there are shear waves and goldstone modes. So these are a set of modes whose frequency go to 0 as Q equals 0. Okay, that's the best way to define them. And they store this. The goldstone mode sort of restores the initial symmetry, if you want. Okay. So broken symmetry is a very general principle of condensed matter physics. I should have written 3 here. Any questions on this? So you see, for the superconducting state, it will be the same. We will have a phase that we will fix, and that phase will be rigid. And when we try to have this phase, to change this phase, well, the phase is conjugate to particle numbers. So there would be a supercurrent. So that's important to see that this is much more general than the small examples I've given here. Okay, so let's see what we just said implies for the free energy, or for tunneling. And that will teach us another important result. So here in this water ice problem, I have it's the free energy that I need to minimize. So let me write the free energy F as a function of some parameter. I will write some general parameter G here. It could be temperature, for example. So the free energy, let's draw it like this. So you see, that could be the free energy of water in terms of, for example, the temperature or some parameter. And that's the free energy of ice. So what happens? We always want to minimize the free energy, right? So there will be a phase transition at this point. because here it's the water that has the lowest free energy, and here it's the ice. Okay, this should be inverse temperature if the ice is there. So now you see that you have the ice. I drew this here because there's a solution that is still ice, even if I'm at a parameter that's below here. And there's a solution for water, even if I'm a G where there should be no water. So in other words, I have a metastable phases. And that so this is a first order transition. And in first order transition, there are metastable, there are regions of metastability. So in the same way that what we found at the Mott transition, there are two solutions here. So that's the thermodynamic transition here. And this region here is a region of metastability. And what you see here is that at the transition, the entropy is equal to minus the F dt, right? So if this is a temperature or inverse temperature, the entropy is discontinuous at this point. So the first derivative of the free energy is discontinuous. So that's called a first order transition. Now there's another possibility. So it's a function of some parameter G, where, oops, I'm exaggerating here. But, okay. So there's a point here where the curvature has changed discontinuously. Okay, so the first derivative is continuous, but the second derivatives and actually all higher order are discontinuous. So in classical, in Landau theory or classical theory of phase transition, there's it's the second order derivative that's important. So it's called the second order transition. But because of the theory of critical phenomena, it's better to call it a continuous phase transition. Now, one thing that's important is that you see if the entropy, or here it would be the specific heat, second derivative, are discontinuous at some point, what does it mean for perturbation theory? In perturbation theory, you're expanding in powers of something, right? So you have some analytic expression of some sort or other. So perturbation theory, in this case, actually, where in this case, at this continuous transition, the correlation length that we talked about earlier becomes infinite at that point. And the same way, the perturbation theory diverges at this point. So that's a singularity. And perturbation theory may diverge because you're expanding in terms of some crazy parameter that's not the right one. So that's just because you're not clever enough. But here, there's no choice. There's no perturbation theory that will get you across this point. Similarly here. Here, the correlation length will not be infinite at the transition, but if you do perturbation theory, you will keep moving like this. Okay, you can never go with perturbation theory from here to there. So we will need to do something drastic, which will be this order parameter. And the symmetry we will need to break by hand in some ways. Now, the other comment is about tunneling. So suppose I'm doing everything at 0 temperature now. Suppose I'm doing everything at 0 temperature. Now, I will not draw this very skillfully, but so this is a nitrogen atom, and I have so this is the NH3 molecules, okay? So that's ammoniac. So why is this guy on top here? This is flat here, this H3. So it could be here or it could be there. Okay. But to go from here to there, there's from this top position to the bottom position, there's a potential barrier. So this is the potential barrier for so as a function of position, R. This is the potential barrier for the nitrogen atom. So the ground state is the symmetric combination of being here, right? Because you can tunnel here. So the ground state is that you have equal probability to be here and there. You can also build an anti-symmetric state. So the anti-symmetric state will be higher energy. Now, if the nitrogen is here, it's because you're doing a linear combination of these two guys to put it there. But this is not an energy eigenstate, so eventually it will tunnel over there. But now you see that there's a potential barrier and there's some tunneling involved. So if you put, for example, the same molecule, but you put a heavier element here, what will happen? Well, or a lighter one. Let's put a heavier one. For a heavier one, this barrier will be higher, these states will be closer, and it will take longer to tunnel. Okay. So if this atom is heavy enough, it will never have time to tunnel. So, for example, if you have a big sugar molecule that is right-handed, in principle, it can tunnel to the left-handed state. Okay, because the two states are they have the same energy. So it's being like here to there. But it will never happen that the sugar molecule, the big sugar molecule in the that is right-handed, will tunnel to the left-handed, just because it's so big and these levels are so close that it takes forever. Okay, so there's something similar here. So here, in a sense, when things are big enough and the energy scales are big enough, you lose these. You lose the symmetry. So you've broken this up-down symmetry here because you put it in that state at the beginning and it cannot go to the other one. Here, if you look at the partition function, Z equals sum over microscopic state of e to the minus beta R minus mu n R, where R are microscopic states. You see, as a function of temperature, there should never be a discontinuity here. You're just adding exponentials that are very well behaved in terms of beta. Let's take G is about the beta here. So how can you get a discontinuity like this or like that? You can get that only in the infinite volume limit. Okay, so there is a question of inverting the order of limits here. So we take the limit of infinite volume first, And then we do these calculations. In the same way here as if you break the symmetry by hand, again, you have some small potential that chooses that the nitrogen is here. In the case of the ammonium molecule, ammoniac molecule, it will do that. I mean, it has enough time to tunnel from one to the other. But if it's a big atom, if you choose one side, it will stay there, just because the tunneling takes too much time. So in some sense, here it's the infinite volume limit is important, and here it's sort of in quantum mechanics, it's sort of also the infinite volume limit. But what I'm saying is that in the case of molecules, these tunneling barriers are so big that you don't need the infinite volume limit in some sense. But you need the infinite potential limit if you want. You need the tunneling probability to be extremely small. Is that clear? Okay. So now how can we put this in mathematical language? So I will work with the ferromagnet, but later. But now I will keep it a little bit more general. Okay. There's a concept of an order parameter. So let's look at ice, and let me look at the limit where n goes to infinity of the density at point n times the lattice spacing correlated with n at position 0. What will it be? Well, what will it be equal to? Well, it will factor even in the n goes to infinity limit. Even if this point is infinitely far away from the point 0, where this, has a small, you can think of this as having a small external field that has pinned the origin. This will factor into rho of NA times rho of 0. So to be more precise here, I should look at deviations compared with the average. Okay, there can be some average density. So I have something that goes like this, and so there's some average density n, and then there's some oscillations. So this is just a statement that if I know the position of one atom at 0, I know the position of an atom anywhere. And that's the order parameter. That's the thing that breaks the symmetry. I mean, or that I should say that is different from 0 in the broken symmetry state. So you see, if you were in the symmetric state, where you have recovered the translational invariance, then these deviations would be 0. Another way, let's look at the other case, the case of the magnetization here. So if I look at limit n goes to infinity of the magnetization along the z direction, NA, times the magnetization according to z at point 0, then this goes into the expectation of mz at NA times mz at 0. Okay, that state here is there has to break the symmetry, because this rotational symmetry, right? Because if the state that is involved here, the vacuum from the point of view of, or ground state from the view of quantum mechanics, at the full symmetry of the Hamiltonian, then this could only be 0 because it can point in any direction. So that's called an order parameter. The definition is not unique in the sense I could multiply this by 4 or multiply this by the interaction, or I can do a number of things. So this is, again, the order parameter is anything that has a correlation function in such a way that if I go to infinity, then it factors this way. Okay, now what is Landau theory? So Landau theory now tells you that there's a free energy functional. Let me try a different symbol. So f of the order parameter m, I take this example here of the ferromagnet, and I write little m instead of mz. Okay. So f of m, which is an analytic function of this order parameter. But here the order parameter is a vector. So when I write m, I mean the magnitude of the magnitude of this vector. Okay, so m dot m. And then I can put an external field plus h dot m. Okay. And this is an analytic function of this. So I can write b over 4. So that's for the now a and b, I don't know what that is. And I write m dot m square. Okay. So this is a functional in the sense that the free energy will be the minimum of that functional. Okay. So m is like a variational parameter, and this is the thing I need to vary. And the free energy is where the minimum of this quantity is. So h is the external field, and since m is a vector and f is a scalar, that these are the only possibilities. I could go to order m6, m8, whatever. I mean, I take that f, the functional is an analytic function of this order parameter. So remember, we're looking at Landau theory, or I should have written perhaps on top. Landau. Okay, so now let me take, because I have this field here, I will take the m will be in the direction of that field. Okay, that I will put a minus here, so that will certainly minimize the free energy if m is in the direction of h. So let me get rid of the vectors now, because I have chosen the direction of the little h. And now I write this as a m square plus b over 4 m4. Okay. So this parameter m that was 0 in the symmetric state I'm saying, okay, I'm giving now a liberty to have this M, and let's minimize this to get the real free energy, not the free energy functional, but the real free energy. So I minimize this, I get AM plus B M cube is equal to H. Okay. Now take the limit. So now take A less than 0. And H equals 0. Okay, H has done its job now. It has chosen the direction. So now I put it equal to 0. And what happens? You see, I will find that M times A plus B M squared equals 0. And if A is less than 0, it has two solutions. M equals 0, and this whole thing equal to 0. You see, I take B larger than 0. Because when the order parameter is too large here, I don't want this to be. If B was negative, I would be in trouble, right? Because if B was negative, M would be infinity at the minimum. So I take B larger than 0. So you see, if A is less than 0, then there's a solution. There's a spontaneous symmetry breaking. H has chosen the direction of M. And now M can be different from 0 just because of some internal physics here that puts this A negative. So these concepts of broken symmetry are present in high energy physics also. So if you look at the forces of nature at high energy, forget gravity. At high energy, they're all the same. And then as you lower the energy or the temperature, if you want, then the symmetry between the forces is broken. And they are even, the particles are massless. And you have the Higgs boson that is one manifestation of broken symmetry that gives the mass to the particles. So these concepts came up first in condensed matter physics, in particular in the context of superconductivity, and they were taken afterwards in the field of high energy physics. So these are all emergent concepts, if you want, because they show up in the limit where the size of the system is infinite. So is that okay? Okay. So now I'm going to use the variational principle. I'm not going to prove it. For now, I prove it. I thought I could do it at the end of the class, but it's already 15 to 11. So I'll prove it next time. It's again a few lines to prove. So instead, I will look at the. I will use it directly for the ferromagnet. So the principle is that minus T log Z, which is the free energy or the Gibbs free energy, is less or equal, so it's a minimum of the free energy computed with some other Hamiltonian or some other density matrix, plus the expectation of H minus H0, where H0 is the Hamiltonian you've used to compute this, evaluated in the basis 0. So I've not proven this, but let us assume that this is true. I will prove it next time. The proof is there. So it means that I have here that the free energy F, this is the one I'm interested in. I need first to tell you what H0 is. Okay. So H0 does not have the symmetries of H. H is my real Hamiltonian. Okay. But H0, I will break this symmetry, this up-down symmetry. So I will write for H0, I will write sum over K sigma of zeta of K sigma C dagger K sigma CK sigma. And now I will allow, you see, the energy of up and down electrons to be different. Normally, when I write this Hamiltonian, the energies of up and down are the same. So it has rotational invariance. But here, I allow the possibility that it's not rotational invariant. So let me put a tilde to make this even clearer. So let's see this here. So I will need to minimize the right-hand side here. That's the whole game. Minimizing the right-hand side will be, it's like finding this xi tilde. So I will differentiate with respect to this xi tilde. So F is less than or equal to the free energy computed with this Hamiltonian. But this Hamiltonian is not interacting. So the free energy, I know, it's equal to minus T log Z, and Z is the product over K and sigma. As usual, run out of steam by that time. Not me, but the, the pen. Is the product of 1 plus exponential of minus beta xi tilde of K sigma. Because for every state, it's either empty, so there's a 1, or occupied, e to the minus beta. And the partition function factors, because every spin is independent, every K and every sigma is independent. So that's really the partition function. And then I get the log here. And then I have plus H minus H0. So plus, okay, H minus H0. So there's a piece that will be sum over K sigma of zeta K minus zeta tilde K sigma. Okay, the original Hamiltonian does not have a sigma dependence does not have a sigma dependence to K, to zeta K. So I take this expectation in this with this Hamiltonian 0. So the H minus H0, that's the kinetic, but there's also potential energy here in H, not in H0, but in H. So at the potential energy, we're working with the Hubbard model. So it's plus U sum over I of Ni up times Ni down, right? Because it factors. And if this Hamiltonian is not interacting, and I'm computing the expectation of Ni up and Ni down with this Hamiltonian, so it factors. But this is evaluated with this 0, so Ni up is not necessarily equal to Ni down. Okay, now let's do the derivative of this with respect to zeta tilde K. So the derivative of the first term is minus T, 1 over 1 plus e to the minus beta zeta tilde k sigma, and then now the derivative of this exponential. So that's again exponential of minus beta zeta tilde k sigma, and then derivative of the arguments here is minus beta. Okay. And now I need to differentiate this term with respect to zeta tilde k, which is my variational parameter. So when I differentiate this, I have minus c dagger k sigma ck sigma in this broken symmetry Hamiltonian here. So that's this. And I also need to differentiate this because this expectation value depends on zeta k tilde. So I have a first term. So basically it will be related to this derivative. I will use the fact that this is equal to u sum over k of n k up times n k down 0. Okay. Why is that? It's a Parseval's theorem again. Okay, I have the same position and I go to wave vector and I use n of k is equal to n of minus k. Okay, so this is C dagger k up, C k up, and C dagger k down, C k down. So if I differentiate now with respect to this, what do I get? I get zeta k minus zeta tilde k sigma, and then I get plus u times this whole thing I want to multiply by the derivative of C dagger k sigma ck sigma with respect to zeta tilde k sigma. Okay, that's what I'm doing. So I need to differentiate this also. So that's this derivative. So I will be left with just this guy, and again using the translation invariance, this can be written as u n of n down basically, and minus sigma. If this is n, if this n sigma, this is n of minus sigma. So I'm using the fact that sum over I of C dagger I Ci sigma is equal to sum over k of C dagger k sigma ck sigma. So now you see what happens is that this here is equal to 1, right? And this, if I multiply by e to the beta zeta k tilde, this becomes 1. And in the denominator, it becomes this. And these two terms are equal. And they have opposite sign, equal in magnitude, opposite sign, they vanish. So I was taking the derivative and I want this derivative to be 0. So the way to do that is to have this equal to 0, the prefactor of this equal to 0. So we are done. So I have that the solution of my problem is that zeta k tilde of k sigma tilde is equal to zeta k plus u and so this is n at site I, n of minus sigma. So this is really like the Hartree-Fock approximation, you see? You recognize this? This is like the Hartree-Fock approximation. So I was mentioning that Hartree-Fock is like a variational result, the simplest variational result. Well, that's what it is. So I'm going to finish with this. I have just a couple of minutes, and we will get a very interesting result.
I just have a question while you're raising.
Yes.
This n minus sigma does depend on the xi tilde, doesn't it?
Yes, yes.
All right.
Yes, very important. Sorry. In fact, I'm going to use it right now.
And it's on site I or on at
Yes, it's on
wave
site
vector
I
k?
or summed over all k, it's the same.
Okay.
Sum over all k and divided by n is the same as sum over I.
Yeah.
So here we have, what do we have? We have that n up is equal to 1 over n sum over wave vector of the Fermi function of zeta k plus u times n down. Right? That's the definition of n up. And n down is equal to 1 over n times sum over k of f of zeta k plus u n up of 0. So now I can use that n up plus n down in this 0 is equal to the total occupation. That will give me what? The chemical potential. But now I have another equation that has appeared now. I have that n up minus n down that I will call n for magnetization is not 0 anymore because I've allowed the symmetry to be broken. So, or we can check if it's 0 or not. So m is equal to 1 over n sum over k of f of the zeta k plus u n up. So here it's n down, 0, minus f of zeta k plus u n up of 0. And now we will get Landau theory. Okay. I assume that m is small, and I will do the power series that Landau has showed us to do. Okay. So, and you see this variational variational approach that I've used here will be the same as doing, I mean, the result of this minimization will be exactly what I get there. Okay, so let's see how it comes up. So it's very easy. I just have to use these two equations. And now I can use that m is equal to 1 over n sum over k of f of zeta k plus n over 2 minus m over 2 minus f of zeta k plus n over 2 plus m over 2. So let me explain. Okay, if I do n is this, minus m, it gives me 2n down. Okay, and that's what I need here, n down. And then the plus will give me n up. So let's do the power series expansion now. So I have m.
So you forgot u?
Excuse me?
You forgot the value of u?
Oh, I forgot u. Yes. I'm so enthusiastic about these minus signs that I forget the important thing. Yes, this is very important. Actually, I'm going to use it right now. U. Okay. So now you see I get 1 over m sum over k of df d zeta k. M is small, so I'm doing the power series expansion times evaluated at zeta k plus n over 2. And now if I expand this, you see I have a first order term that has minus sign here and m times u. Okay, and then the next order term will be m cubed. Okay, because m square will cancel here. So the next term is m cubed. So that I have that m is equal to, what is this? This guy here is the delta function in zero temperature limit, is a delta function at the Fermi energy and with the minus sign. So it's equal to the density of states at the zero frequency times m times u plus order m cubed, which is 0 equals n0 u minus 1 times m plus order m cubed. So this is like what I wrote earlier, a plus, well, I need to find the sign of this. Actually, the sign is negative in this case. So, so this is more like, I'm sorry, this is more like the minus a, 0 equals minus a m minus b m cubed. So when 1 minus n0 times u is less than 0, I have a non-zero solution. And I will derive this result another way next time. Okay, next time I will start from the paramagnetic state, and there was a non-ordered state, and I'll find this. So so what you see is that using the Feynman variational principle, we can set up the solution. I mean, minimizing with respect to parameters, the right-hand side here in this variational principle is equivalent to minimizing a free energy functional. So you see, this becomes with this 0 that I don't know here, this becomes a functional of the magnetization as I have shown here. Okay. Okay, so now I see you Wednesday. Okay, it's far away. Try not to forget everything. But I will start by proving the variational principle here. But what I have shown here is what we call the gap equation, and at the same time, the Landau theory. This is the gap equation. Okay. Any question?
Yes. I didn't understand how you got from the sum over k of the derivative of the Fermi function divided by n to n0.
You want me to explain this?
Yeah, maybe just quickly in a few
Yes,
words
yes.
why.
Okay, this is the derivative of the Fermi function is like a delta function at the Fermi energy as the temperature goes to 0. And I need the minus sign here to get the delta function. So if you transform the sum over k as to an integral over energy times the density of states, this will pick up the density of states at 0 at the Fermi energy.
All right, okay.
So n0 here means density of state at the Fermi energy. I'm going a little bit too quickly now. I'm sorry.
Yeah, okay. Thank you.
Okay. Okay, so I will stop the recording. If you have some questions, you can stick around and I will try to answer.